So welcome everybody to this Big Data at Chalmers event. We have a regular series of such events, tech talks and technology updates, but this one seems to be really special given the amount of interest it generated. The audience we have here is fantastic, and also the event is being live streamed, so it's really great to see the response here. So today we are going to have this discussion about artificial intelligence from a blank slate. And it's going to be in roughly 3 parts. So the first part is going to be about this recent breakthrough from DeepMind, AlphaGo Zero. And Mikhail Kogobek here, who is a PhD student in our group, who works on some of these techniques. He will talk about it. And then he will also talk about some of his own research in the area. So the second part of the talk, we will also mention some other work in research in related topics that go on at Chalmers. So Mikhail will talk about his work, and then we are very happy to have Nasser Mohammedia from Zenuity, which is one of the hottest things happening in Gothenburg these days. And autonomous driving, this is another big area where these techniques are going to really make a big impact in everyday life. So that's going to be the rough plan. We'll more or less, without any further ado, get underway. But I should also like to invite you all to stay back after the event to have coffee and mingle. So if you want to stick around and talk with some of us after the event, there's going to be coffee. So please stay after the event and talk to us. So after Mikhail's first part talking about AlphaGo, we'll have a short round of questions, and then we'll continue with the second part of the event today. Over to you, Mikhail.
Thank you. See if I can find my clicker. So, you are all very welcome. I'm not really used to this. They don't usually let PhD students on this stage. But it's nice. I guess it's partly because today it's not only academics here, it's not only people from Chalmers. I can see some people from industry all over. And also, actually, I heard that there's people from the Go playing community here as well. I don't know if you're here or if you're via the live stream with any. Regardless, hi. And I will try to keep this at a technical level that it should be possible to follow even for computer scientists. Okay, so first off, this game of Go. It's a very, very simple game in the sense that it's not many rules, but it's really complex in some other respects. So the game is really about putting stones on a board. You have 2 stones or types of stones. You have white stones and you have black stones. But you can't choose which one to play. You either play white or black. So you're 2 players and you go back and forth and put stones on this board. Okay. You can capture your opponent's stones by surrounding them. So either a single stone, so here black has surrounded white and captured that stone, or you can capture a group of stones by surrounding it. So if your group of stones have no way out, then they're captured. But this is, if you're a beginner like me, then that's really all you focus on, usually, trying to capture stones, but it's really about capturing areas of the board. So here you can see, it's kind of difficult for me, but white has kind of captured this area, black has captured maybe this area, white maybe like that. So this is like towards the end of this game. And there's, as you can see, there's so much complexity here. It's been written many, many books. This has been played and studied for over 2,500 years, even though the rules are so very, very simple. So in a way, it's like almost like biology. You have this one cell that kind of divides and creates a human being. But in this case, it's, well, not a human being, but still a lot of complexity. So this is the game of Go. So there are some properties that we can use to solve it. First of all, it's a game of perfect information. This means that you you know everything all the time. So just looking at that board up there, even though it's confusing if you're not a Go player, it actually has the complete state, more or less. Okay, you have to know who is playing as well. Except for that, it's more or less the complete state. So you don't need to know anything about the history. Just looking at that, it's fully observable, and it's perfect information. So you can compare that to poker, for instance, in that there you do not know what cards are in the hand of your opponent, so you need to do something else, another algorithm. For this, you have perfect information, and that is important. Secondly, there's a discrete state space, action space. This means that even though you can choose between about 250 different moves at each level, they are still discrete moves. You can compare that to, well, what Sinuity will talk about later, which I guess might have something to do with self-driving cars, where you have a state space that isn't discrete. I mean, you can turn your steering wheel arbitrarily. Okay. So some other games that have these similar properties, chess, for instance, and actually also tic-tac-toe or trirad. And I'm going to use tic-tac-toe a bit as an example because it has another similar property to Go that you can actually rotate it and reflect it, and it's still the same board. And that is something you can use. Okay. So these types of games can be seen as a tree of possible games. And that's something, that is how you solve tic-tac-toe and can solve tic-tac-toe, and that's also how you solve chess. So you can think about this tree starting with nothing, and then someone puts a cross either in the middle, on the side, or in the corner, and then these are rotations, so you don't need the rest. And then you continue by putting a ring somewhere, and you have a tree. It's going to be exactly 9 levels deep, and it turns out that it is about 26,000 different games that can be played, which was more than I thought, but I Googled it, so Wikipedia said that. So it's probably correct. But it's still, it's okay. You can search this complete tree, so you can go, okay, if I start here, then I will win more often than not, so then I will select that. However, with Go, it's a slightly different story. Even though this is still perfect information and you still can potentially search this entire tree, at each step you can select between 250 different moves on average. Which means that you have a branching factor that is so high that it will completely explode really quickly. Even if you just want to search like 3 or 4 moves ahead, there's too many possibilities. You can't do that. In practice, it's more or less infinite. Or at least we can't do that with computers right now, which is why people thought we wouldn't solve Go right now. But we did, and there's a reason. Okay, so the number of games that you can play, they're actually way, way more than the number of atoms in the universe. Way, way more. So, yeah, I just wanted to put that in. Now, maybe you could help me. Be non-Swedish and shout out. Where should X play next? Yeah, great. That's quick, very good. Okay, so now you're in it. This time I want to hear everyone. The next one is going to be slightly more difficult though. Okay, are you ready? Come on. Bottom left, thank you. Maybe top left is okay as well, I don't know. But bottom left, if you play there, they're going to win because, well, your opponent can only stop you once. So my point here is that you who did say bottom left, awesome. So you probably didn't iterate all of the different games. So there's 1, 2, 3, 4, 5 positions left, which means that there are about 5 faculty times number of games you can play here, which is about 120. And I don't think you simulated them all in your head. You used something else, some kind of pattern matching. So you probably didn't start like trying this one, and then, then my opponent would do that, and so on. You used some kind of intuition. And you used your neural network. So let's see if we can use an artificial neural network to do something similar. Okay, so what is that? All right, here's a cat and a dog. So the nice thing with a artificial neural network, or this is like a feed-forward convolutional type of neural network, is that you can train a function to map from some kind of image or some kind of input into some kind of output. And you do that using examples. So maybe we could do this instead. Maybe this is from the paper, so they did do this. But okay, so instead of a cat and a dog, you have this board. And instead of having a segmented image, you have, well, potentially good moves. So this could be because some human suggested that this is a good move by just looking at gameplay. And you could see that these are good moves, or it could be something else. So both of these are learnable functions that can map from an arbitrary input to an arbitrary output if you just have some kind of examples. Okay, so you could ask yourself if we're done now, but according to my timer, we're not. Okay, so what's missing here? Well, for once, it's examples, right? So DevData told us that we're not going to use human knowledge, so we can't have examples. So they used examples last year, but not this time. So instead, they use self-play. So just playing against themselves to generate examples, and then use those examples to train the network. Well, so that's one thing. We don't have any examples. The second thing is, okay, so where should White play next? Come on. You were real quick last time. Could you? Okay, so I'm not a Go player. I mean, I played a few times. I usually lose, but I would say, okay, maybe somewhere in this region, but, because this region isn't really done yet. So I don't know who is owning that region, but I'm not really sure. Maybe there's a better place to start. My point is, I have an idea of where to start, even if I'm not a real Go player, but I don't know exactly, so I would have to reason about it. So maybe we could use this intuition together with some kind of reasoning. So we can't try everything. I'm not gonna simulate what happens if I do play there or whatever. But maybe we can combine it. Okay. So the following 2 slides are going to be the technical ones. Please bear with me. But this is actually where you will learn how this works. And there's only 2 slides. It's not a lot. And it's not that difficult. Okay, but in order to understand this, we will need to explain what these Q's and U's and P's and whatever are. So I'll start with that. So Q in this formulation is it's called the action value. So Q, starting at some state, the state is the board, how the board looks right now. You take some action. So each of these arrows here represent one Q value, one Q for a certain state and certain action. And that is the value, the average value of all the boards underneath. And the value is the approximate probability that you will win if you end up in that state. Okay? So the Q value for going here is going to be the average of the value from here and here, and they are like approximations of how likely you are to win there. Okay? U uses this intuition thing I'm talked about. So the suggestion of good moves. So P here is a distribution, or it's a You don't need to necessarily think about it as a distribution, but rather this, right? So this is apparently a good move. So this is what P is. We can think about that as a distribution because it sums to 1. Okay. Now, V and P, you could ask yourself where we got those from, and that is using this neural network that we're going to train. So you actually input the state, and then you compute these approximate values and approximate like good moves starting from that state. Okay, so now we have all the tools we need. Now we can do the fun part and just walk through this tree search, which is called Monte Carlo tree search, if anyone cares. It's MCTS. Okay, so it's an iterative type of search. We start with A. Now this, in this picture, we have already started the search, so it actually opened up 3 nodes already. So we start at this stage, which is the board currently, where I wanna, where I wanna choose my move from. And then I traverse this state, so I go to the maximum Q plus A, so the maximum average value plus this U, which is connected to the probability. Sorry, you never told me. Why didn't you tell me that I didn't give you N? Should have. All right. So N is the number of visitations. So you simply counting the number of times you have traversed the tree down that route, because you don't want to traverse the tree exactly the same all the time. If you have done that for 1,000 times, you maybe want to try something else. Okay. So you traverse this tree until you reach a leaf. Now you want to go in this direction, but you haven't opened the node yet. So we go to B. Now you evaluate this. You open up a new node. So you're starting at that position. You play the move that you wanted to play, and then you push this state through this network and get a new P and a new V. Okay? And then you back up because you want to update these Q values. So you want to have the complete average of everything underneath. Before, it had an average of that one and that one. Now you want to add that one as well. So the Q is actually the average value. And then you repeat. Rinse and repeat. And you do this during training about 1,600 times. When you actually play in a match, it depends. It can decide when to stop. So you can continually search until you think you have found something, an acceptable solution. So, but during training, 1,600 times, and then you choose to play the move that has the highest visit count. So you actually compute this pi by just taking the total number of n's. So that's going to be, if you play it for 1,600 times, it's going to be 1,600. And you divide each of those numbers by 1,600. And then you get something that looks like a probability distribution, pi over good moves. Okay. So that was the first slightly difficult slide. Was it okay? You look, no one is asleep, no one is dead. Okay, good. Yeah, sorry? So we update P in the sense we're going to update the network, so next time you see P, it will be something else if you have trained the network. That will come on the next slide. But otherwise, you will not update it during the search. Okay, so training of P and V. I kind of gave you P and V, this magical neural network that just gives you the value, and this P is nice, but how did we end up with a good such network? How did we train that network? So now you need to take a small step backwards. This was like the reasoning part of the algorithm. It's going to be integrated into the reinforcement learning framework now. So take a small step back. Well, you can't do that because you're sitting. But think about taking a small step back. I can take a small step back for you. Okay, so we start at the top, A here, the self-play. So the self-play continues like this. You start with a blank board, of course. That's how you play a game. And then you do this Monte Carlo tree search, and you ended up with these pi values. That was the last slide, right? Now, from these pi values, you select an action. You sample an action. So if you're playing in a tournament, you are most likely going to choose the maximum, like most probably good action here. But during training, you can think about it. If you're playing a game of Go against your pal, then, well, you have won so many times already, so maybe you want to play something a little bit suboptimal just to explore, to kind of, all right, it looks good, but I'm going to try that. And this is important for you to learn, to explore a little bit more strategies. So you actually sample it. You add some temperature to that probability distribution, and then you sample from it. So you do that, you select an action, play that action, and now you're playing as your identical weird schizophrenic twin because it's self-play. So it's actually the same network playing against itself. You have to keep track of that, of course, in the end if you won or lose, depending on, which one of yourself you are. But except for that, it doesn't matter. So it's just self-play, so you select a new action using this Monte Carlo tree search. You sample an action, you play it, and you do it until both of the players pass. That's how a game usually ends. So they say, I don't want to play anymore. Okay. Then you score the game using quite complicated rules, actually, that I'm not going to go into. But it doesn't matter. It's like part of the game. So you score the game, and you get like either 1 or -1, depending on if you won or didn't. So that's the self-play. And you do this for loads of times using this neural network inside of your Monte Carlo tree search and generate games. You generate data this way. And then you want to go to the neural network training. Now, the network will start with V because that is very simple and standard and straightforward. I mean, you have this Z value. These V's here suggested who would win. So if they were wrong, you better update your parameters, right? So you do that. You simply backpropagate these Z values into V and through this network. So you update your network, not so it's like, okay, given this board is now always going to say you win because it said you lose before, but it moves it in that direction. So it's not a hard thing. It's a soft kind of moving of the prediction. So you do that. The second one is, I think, maybe the key to why they were able to do this so well and so quickly. Because now you have to so the intuition here is we want to update these p-values. We don't have a human who can tell us what a good move was. So they trust their reasoning. Okay, so you have a network that you use inside of a Monte Carlo tree search, but it turns out that if you use that information and also do a tree search, so then you will end up having a much better understanding of what is a good move. So you have this. You use this intuition that you have stored inside of your network to guide the reasoning inside of this Monte Carlo tree search, but then after the Monte Carlo tree search, you have a much better guess. So now you update your network so that next time it sees the same board, it will actually perhaps give you the optimal tree search thing immediately, and then you will start from there, but you still do a tree search. So you do this over and over again. And this is kind of reasonable. I mean, when you play yourself, if you have some situation and you think about that situation, oh, should I do that? Should I move that? Well, if I move that, then my opponent's going to do that. Ooh, that was bad. Then I update my intuition so I'm not thinking of doing that again. Make sense? Cool. So more precisely, they train this P from the Monte Carlo tree search pi. What they got here, they update this P part of the network. And it's actually one neural network, and they're making a big deal of that. So they could have had two neural networks, one predicting P's and one predicting V. They had that a year ago. Turns out it's better to use one and then just predict both. So this is called policy iteration. And I would guess that there are a lot of people here that have seen like that TARI thing and maybe the DeepMInd paper about AlphaGo from last year and many other papers recently in deep reinforcement learning. And they are usually in things like A3C or deep Q learning. I'm just saying a few weird things, so if you haven't heard about this, you don't need to care about it. What I'm saying is that this is slightly different. And if you think about it, it's kind of weird. We don't do any optimizing future rewards, so on. Well, implicitly we are, but we're not doing it directly. But then again, policy iteration isn't new. It's from the 50s or something. But they did it in a new way using this Monte Carlo tree search as a policy evaluation operator, which turns out to work really well. So some of the results. So you have two versions here. The supervised one is the same algorithm, but where they allowed it to see human moves as well. So they pre-trained it using human data. And it learns more quickly, but quite fast. We actually see that the reinforcement learning one outperforms. So this is kind of weird, but it turns out that it probably is because it ends up in a bad local minima or something, and then it can't get out of it. So the pure reinforcement learning one actually, even though I would think it's strange that just because someone gives me some kind of tips on how to play, I will end up being worse off than if I just played myself. But that is what the data are telling us. This dotted line is the exact version of AlphaGo that beat Lee Sedol, the world champion, 1.5 years ago. So it turns out that after only 36 hours, this reinforcement learning, this pure reinforcement learning algorithm is on the same level as the world-class Go players without having ever seen anyone play Go. So it reinvented like the strategies, and they actually show that a little bit. But since I don't really know how the strategies in Go works, I'm not going to go through them. But they actually reinvented a lot of those strategies that you can read in books on how you should play Go during those 36 hours. And after 72 hours, they won 100-0 against this program that beat Lee Sedol. So it's clearly better. So we kind of wrote the book on Go in just a couple of days, and invented new ways of playing that the human race didn't figure out in 2,500 years. That's pretty cool. Okay. So this shows how well it predicts how a human plays. So it's interesting to note that the supervised one, the one that is trained to imitate humans, it actually predicts moves better than the reinforcement learning one. So it's better at predicting what a human would do. It kind of makes sense, but it also tells us that, or it indicates that since this reinforcement one is better than the supervised one, we are dealing with, it's playing in a quantitatively different way than a human would do, right? And finally, this is the value function, how well it predicts whether or not it will win from a certain board. And as you can see, when it becomes better, it is actually also better. So here you want a low mean squared error. So it predicts the outcome much better than the supervised one. Finally, if you train it a little bit longer, for 40 days, which is how long they trained the original one, I should also note on the computational power side that the current one is not like they bought a new cluster and is therefore quicker. The old one was trained on, what I don't remember now, like 170 something? Did someone say something? 48 TPUs and something GPUs as well, if I remember correctly. Okay. The point is, it's a much, much bigger computer. The AlphaGo Zero is on one computer with 4 TPUs, so that's like equivalent of what's under my desk. Probably slightly better than what's under my desk, to be fair, but still not something extraordinary. Okay, so this master one is more or less the same algorithm as AlphaGo Zero, but trained with supervised learning, and we have the same story. It actually reached a very high level. So this master, AlphaGo master, was competed against human players over the internet in January, and it did like professional players, and it won 60 matches to 0. So it's a good, strong Go player. Was the best Go player before AlphaGo Zero, but AlphaGo Zero now beats this master with 89 to 11 out of 100 matches. So it's a very strong Go player. It's also interesting to note that this one, the raw network thing, we discussed that before when I just show you the image and I wanted you to, what would white play? So that is doing that. Just having the feed-forward kind of neural network thing, just doing whatever it suggests. It's not as good as this, but it's still almost at the same level as the European champion, right? It would beat the hell out of me. Then again, my smartphone beats me very easily in Go. So maybe I'm not the good comparison. But anyway, that's pretty impressive. But you can do better by thinking about it. So this is all I wanted to say about the Go part. So if you have questions now regarding this AlphaGo, please go ahead. I think there will be a mic passed around.
Two slides ago, I think it was, titled Empirical Evaluation.
Is it?
Yeah, that's the one. We see after about 40 hours on the graph to the left that there's a sudden jump on the reinforcement learning version.
Yep.
Is it possible to interpret that jump?
Well, you usually see this. I think this is an extraordinarily smooth curve. It's kind of common that you have these jumps, and it comes from it figuring out some new strategy, something that had not been tried before, and then all of a sudden it uses that strategy and gets a jump. That's usually how. So you usually see that in reinforcement learning.
Yeah. So the question is, could one see what the actual jump is? Could we interpret it as humans to see? Okay, so we have found this concept or this strategy or this pattern.
Maybe, yeah. So I didn't include that in this presentation, but they had a timeline with different strategies being invented at different points in time. So you could, if you look in the paper, you can see that. I'm not good enough at actual Go playing, so I can't really talk too much about that. So, yeah, thanks. Good question.
On that slide, you see that the reinforcement learning one passes the human because the human started from some preconceptions, basically. Did they try to restart the reinforcement learning from a new random state and see if they get another curve?
If you randomize it and restart it and not do any supervised learning during it, then you would. Then we would have this state, right?
Or maybe it could end up in another state that's slightly where that jump that we talked about just now is perhaps different.
Okay, so maybe your question is, if you do this many times, would you get a different result? So that's a very good question. I would hope, and I guess, that these are averaged, but it has to be averaged, right? Yeah, it would be weird if nature accepts them and it's not averaged. So usually they're averaged over 10 or 100 runs or something. Yeah. Yes.
one imagines that it only knows the rules of Go, and then somehow it finds the strategies itself, right? So could you do it with the same network but a different game, like chess?
Yes, I would presume that you can.
But you know if they tried this, it's an obvious thing to do.
So I'm not. Yeah, that's a good question. I haven't seen that they have done chess using this. There are some very few things that I actually do that are Go specific. So since Go is rotational and reflection invariant, you can start playing in any corner and so on. It doesn't matter. Whilst chess, I guess, it has some kind of idea of how the board is laid out. That could be a difference. So when you train these networks, you actually reflect them and show it to the network in different rotations and different reflections. On top of that, there is one rule that says you can't repeat a board state. So you're not allowed to do a move that makes the board look exactly as it had been in the past. So in order to be able to deal with that, they actually include, I think, 8 moves back or something of boards. So that could also be something that's different from chess. I think that's pretty much it.
So you haven't told us much about the actual architecture or structure of this neural network. For instance, the network that computes the value of a position. How big is that? How many possible evaluation functions can it describe? Like, what's the capacity of this?
Okay. So yeah, I didn't want to include too many details. I can give you the gist. It's a residual network. So that was it's a type of convolutional neural network that was presented by Microsoft a couple of years back. That has really, really good results on image classification, and they can be really, really deep. So it's a residual network. They have some results where they compare pure convolutional networks with residual networks, and they show that they outperform them. The exact layout of them is in the paper. It's not an extraordinarily deep network. So residual networks can be like 1,000 layers deep. It works because they have skip connections. It wasn't that deep, but if you want to discuss the exact numbers of the filters and so on, we can do that over coffee, I think.
And just a rough estimate, like how many bytes, kilobytes, megabytes, gigabytes?
The number of parameters.
The storage capacity of that.
I don't really have that figure in my head.
I don't have any feeling how big that have to be, right, for that.
Should we? Maybe we should do that afterwards. I don't know. Sorry.
So maybe, in the interest of time, we go over to the next part, and then we can take more questions later, and also also over coffee.
Yes. Thank you. So. Thank you very much. I'm going to stay, though. Just so you know. Okay. So what else could you do? So I just want to show you something fun that I did together with a master student, or he's no longer a master student. He might even be here. I think I saw him. Emilio. Ah, there you go. It's at Fraunhofer now. And Emil Gustafsson. Anyway, so what it's about is, okay, so we can play Go, that's fine. But it would be interesting to see if we could create some kind of communication between robots, we thought. Okay, so currently, if you think about how a chatbot, so this is like the Google, maybe you've seen this on YouTube. I think they live streamed it for a while. There's 2 Google Home units that talk to each other, and they have a weird discussion. So these types of systems, they're really more or less lookup tables. They can be really advanced lookup tables, but they are still just reacting to what is being said. They don't really have a purpose. They're not trying to communicate to solve a task. So we thought, if we give them a task to solve, would they start communicate? All right. So we went for Guess Who. You may have played this, hopefully not too recently. Or, well, with your kids or something. That would be okay. So, but the game is about, you have all these pictures, and you have one picture here, and you're two players, and you want to figure out which of these are on your opponent's board. So you have to, or you ask questions back and forth. So you have to ask questions that has something to do with what's on the board. So we gave them nothing. They had no language at all. We just gave them the possibility to send some kind of message. And the network, this is the architecture. I'm not going to go too far into this, but it sends these messages back and forth. So this is the answering agent, and this is the other agent. In the beginning, these messages are just random. But by sending messages back and forth, they, in the end, can guess which of these images are on the opponent's board. And in order to solve that, they have to encode some kind of knowledge into these messages, because there's no shared parameters. They are like complete. This is not self-play in the sense we had before. They are two completely separate entities. So we do this communication over a noisy channel, so you can't send exact numbers. And this is like how language works in reality, and it's probably a reason why we communicate using symbols, because in a noisy environment, it turns out that that is optimal, so words. And then we have let's say, a written exam. So in the end, they can only send discrete words after doing its training. So this is nice, and we could see that, yes, they do actually create some kind of interesting language. I mean, they start by just doing random things, and in the end, they are able to guess with a certain probability, it's not completely optimal, but they're able to solve it more or less, starting from nothing. And I think it's kind of fun. There was like in Wired or something about Facebook having some chatbot that started to create their own language, and oh my God, it's taking over the world, we have to shut this down. It's very easy to get a robot to create its own language, as it turns out. Much, much harder to make it work with human language, because when we looked at the words, I mean, they solved the task, and we can say that, all right, we tried to kind of figure out what the words meant. Well, it looks like it could be black hair, but, well, it's not completely correct. It's a hat, right? There's some white hair here. So there was some features that we could recognize that they encoded into their language. What's going on down here, I don't know. I mean, they are solving it, but it's not clear to me that it's creating a human language. It has some grounding, but not quite human. This was a fun little experiment. This is all I have now, so I'm going to now leave the word to you from Sinuity, Nasser. While you're setting up, if you have any questions regarding this, you can go with that now, I guess.
Have you thought about trying letting this practice playing against a human and see if it would learn communicating with a human in that way? So
if you do that, it would probably learn human language, I would presume. It would be a really boring task, I guess. But if you are, you're welcome. You can come.
I don't know.
Sure.
No, you don't need to insert.
That's a good point.
No problem.
Yeah.
Just put it in your pocket.
You could enroll a bunch of preschool children to play with.
Sorry?
You could enroll a bunch of preschool children to play with.
I have a 5-year-old. I could ask her.
Yeah.
Make an app of it so people can play it on their phones.
You have all the ideas. Thank you.
I will put you on automatically.
Okay.
Okay.
Hello. Do you hear me now? Yeah, I think so. It was a nice presentation, a great intuition, and a very good working algorithm. So how many of you do you think that such algorithm can also solve autonomous driving? Just a few. Or? Making your mind? So I hope by the end of this presentation, I will be able to convey a couple of main differences between what we are trying to do with autonomous driving and this kind of applications with the games and so on. So I'll try to. You had also this thing. Never mind. Yep, here. So I'll try to give some general information about a couple of projects that we have been doing with machine learning for decision and control part. And I will also introduce a recent PhD project that we are running with Chalmers on safe reinforcement learning. In self-driving cars, as you know, we have many different sensors, cameras, radars, lidars, mounted to scan the surrounding of the vehicle, 360 degrees surrounding the vehicle. And this information is processed to control the vehicle. The way that this information is used can be very different. At least two very different approaches is what we call modular system design. Okay. Never mind. Is the top approach. You see that the data from different sensors are collected and gone through different components, different modules that are very well specifically designed to extract some information. For example, the objects, the road information, and so on. That information is then passed through sensor fusion and later on decision and control. We can also think of what we call end-to-end learning to use directly raw sensor information, such as images, to control the vehicle. When it comes to machine learning and self-driving cars, currently machine learning is mostly used for perception data. So, for example, in image processing or LiDAR detections are processed using deep neural networks to extract information such as road edges, lane markings, drivable road, understanding the scene around in the vehicle, or detect the objects. Could be very specific objects such as vehicles or pedestrians, cyclists, or general objects that could be in the traffic but are not there very often. And estimate their distance. On top of that, a little bit more research direction with the sensor fusion, radar, signal processing, and so on. So these are the works that we are primarily working at Zenity using machine learning and deep learning. We are also looking into understanding neural networks and how to balance between real data that we collect and annotate and synthetic data. For the decision and control part, I'm going to give two examples. The first one is a holistic lane keeping assistance system that we have done through a thesis work here at Chalmers, and we got quite good results out of that. So here we are actually doing just a supervised learning using the data that we have collected at Volvo cars, using different expeditions around Europe. And what we are doing is, how do you use this laser? This one. So the input to the algorithm is just a single image from a single camera looking forward. And the output is supposed to be the steering angle. And we learned that by the supervision is that we have this feedback from an expert driver who has driven in the real traffic, and we tune the parameters of this network, which is a deep neural network, to mimic what the driver would do in this situation. So this learning is done completely in the using real data. It's basically IID samples. We don't have sequences. We don't use history and so on. It's just give an image and get an output. What I'm going to show is the results from a simulation environment car maker, and the data that we use in the car maker hasn't been shown to the agent beforehand. So this is completely new data. And what you see is a real road from Rijkswijk here. And I'm going to show two videos. The first one is a night drive, because it's slightly more difficult than the day time driving. And I will also show a fault injection, where we try to force the vehicle to go out of the lane and see how it will react, and will it find its way back to the lane. Now here it comes. So I hope this is clear. So this part of the image is what the network sees, and the rest is just for visualization. And as you can see, this is driving quite smoothly, and we haven't done that much of smoothing and filtering of the output. And there's a big room of improvement if you use a history or you try to filter out steering angles. And this is just supervised learning. Let's look at this one. So right fault injection. And this environment, this information is completely new to the agent. It hasn't seen before such quality images or so. And this is a different simulation environment. Quite nice, I guess. This is another project that we have been doing in collaboration with Volvo Cars in using object-level data. So we have perception modules in front of that are processing the camera images and the radar detections, and then fusing them to obtain objects around us, road information, lane markings, and so on. And then we also use, again, supervised learning and neural networks to mimic what the driver would do, to estimate ego vehicle path. So this is a path, a trajectory that the vehicle has to take in the next 3 to 5 seconds. And we have done different tests here. So this is feed-forward neural network. This is convolutional networks, and this is recurrent networks. And as you can see, we got much better results when we switch from CNN to, for example, to RNN. Although all of them are using exactly the same information, the same history data is constructed in a way that both CNN and RNN see the same information. We are also trying this using generative adversarial networks and recurrent neural networks, but it's still ongoing projects, so I don't have any results to present here now. But what are the challenges and how we should go forward? So first of all, you can imagine that when we are talking about self-driving cars in the urban area, and we are talking about complicated scenarios, machine learning in general can be useful for scenarios such as crossings, the roundabouts, double merge scenarios, and so on, that are complex enough so that the usual logic doesn't really help out very much. But we have to consider the information that we have here. So in game, Mikhail mentioned that we have perfect information scenario. It's not the case anymore here. We don't really know what is happening with the other road users. We could have a prediction, but they could change their mind every moment in time. So that we have to consider. We have to think about safety and be careful about that. I will come back to that later on. And one quite important point is the interaction with other road users. We don't want to have a self-driving car which is very defensive or very offensive. So we don't want to stop in the crossing and wait for all the other road users to pass and then we do something. We would like to act naturally as the other human drivers would do. There are several approaches to, people are looking into different methods using, trying to model how the other road users behave to self-driving car. If we try to cut in, if we try to overtake, how would they react and what would be their response to that? Or explicitly bring safety constraints into modeling. At the same time, there's a lot of work on inverse reinforcement learning and trying to understand, again, the other road users. But how safe do we need to be? We have, we hear a lot about accidents, but not very much about fatalities. They are very rare. Although many people are killed in the accidents, but if you look at the miles that people drive before someone is killed, it's really very small figure. So this is some results from last year, and this is the statistics from US. So this vertical line here shows the fatality rate per 100 million miles. So in US, for every 100 million miles, only one person is killed. And that's really a small number. If you are thinking about self-driving cars and imagining that self-driving cars should be better than humans, we have to at least be safer in this kind of orders, and many more miles than that, but at least 300 million miles and one fatality. If you are thinking about the injuries and accidents, so this is the figures, around 100 failures per 100 million miles. So the conclusion is that the events that are dangerous happen very rarely, and somehow we humans are very good at taking last moment decision that avoids killing someone or getting into, serious injuries. So what is the conclusion from this and implication for reinforcement learning? Without going to these variable names here, so the main message is that if you have an event which is very rare, happens with very small probability, and you want to learn how to react in that kind of scenarios using reinforcement learning, you have to associate a very large negative reward with that output of that reinforcement learning for that in that scenario. If you do that, so say that there's an accident scenario and you say that for any dangerous situation which will be accident, we associate very large negative reward to that. That directly leads to having very large variance for the total reward that your reinforcement learning agent has. That also means that we cannot even estimate the objective that we are trying to optimize, let alone the gradients of that. Therefore, we cannot solve the safety problem by just increasing the negative reward that we give to the accident. It doesn't matter anymore. It will just make it impossible and not a stable solution for the reinforcement learning. So what we are doing, we have a PhD project on safe reinforcement learning here with Chalmers. That's a WASP-funded project. The main questions that we are trying to look into in this project are, well, what is safe to begin with, and how we can plan risk-sensitive planning and at the same time be safe. How we should react with the other road users and take them into account when we are planning. So if we try to cut in or change our lane, the other road users will react in response to our action. And there's also a very hot question nowadays to learn in simulations and to transfer it to real data in real experience, how valid that will be and how to improve the validness of the results that you get in the simulation to real experience. We don't want to learn a lot in the real experience and let the car to be in the real traffic and drive and learn. That will be perhaps a very dangerous situation. Hannes Eriksson is working on this project as his PhD, and we are working in, he started in September. He's also here. We are hoping that by the time that we approach to the end of this project, we are in the good position to also implement some of these technologies in our self-driving vehicles. We are not alone. There are other groups, the researchers who are working on this. This is one approach to look at the problem. So they try to decompose the policy into something that is learnable, to learn what you desire to do, right? The high-level strategical decisions, and the non-learnable parts where you try to map the desires into a trajectory, which is basically the XY coordinates of the trajectory. So in this case, if you look at the double merge scenario, which is quite complicated one, the desires would be like the speed that you would like to have, the the L will be like which part of the lane you would like to be, in the center, in the left, in the right. So if you want to go to the right lane, perhaps you have to change it slightly to the right of your own lane before changing your lane. And how you want to do with the other vehicles. You want to overtake them, you want to give way, and so on. And the driving trajectory will be just optimal control, mapping the desires into trajectories. You could also do kind of achieve safety by including collision avoidance terms explicitly into your modeling. And here this is one work where they try to apply deep deterministic policy gradients reinforcement learning algorithm to combine that with collision avoidance and path planning or path tracking to do trajectory planning for the self-driving cars. This is one very interesting work, slightly difficult to talk about that about the equations. The main message is that people are looking into how explicitly model the other road users and use that model in planning of the ego trajectories. In summary, we see that there is a strong role for machine learning in self-driving cars. It's mainly perception nowadays at Zenuity and many other companies. So that will be very vital in the success of autonomous driving. But if you look at the modular system designs that I showed you, there is also a role for machine learning and reinforcement learning for decision and control. Now it's a little bit specific problems in the crossings, in the roundabouts, in the double lane merge. And maybe in the future, no one knows, we can find a reinforcement learning method that directly solves the whole autonomous driving problem. It will be a little bit too optimistic, perhaps. One point that makes it very different what we are doing here with other applications such as games and so on is the safety. So here we don't have, we can't fail basically. If you are using an algorithm and if you are using this kind of machine learning methods which are optimizing or maximizing, minimizing some sort of average value, we cannot really guarantee the performance of that algorithm. And that is very important for self-driving cars. We have to have an agent which is guaranteed to be safe all the time or very, very low failure rate. I guess that's all about this. I have a couple of other slides, but if you have any other question or we are recruiting all the time, maybe advertisement for Zenuity, have a look at Zenuity website. And if you're interested to do a thesis or any other ideas, please approach us and we will be happy to discuss that. And now if there is any question, I'm happy to discuss.
I mean, you could argue that to be able to drive, you would need some sort of general artificial intelligence. I mean, what if there is some unexpected situation and, I mean, someone put up a sign that, yeah, there are loose horses in 2 kilometers and you can't see them, but they will sort of appear out of nowhere. I mean, a human would see this sign and immediately understand that, okay, I should slow down. Or, I mean, you use a lot of things driving that you don't learn while driving. I mean, when interacting with humans or sort of doing other things, I learn things which I will probably never use while driving, but might prove very beneficial. So how do you view like problems like this?
So I guess the fair answer is that we are not going to solve for all scenarios in the beginning. It will be limited use cases. And we will learn from that deployments that we have. We will learn from that and continue from that. And on top of that, it's not only say sensors that we have on the car that we have access to. Self-driving cars have access to maps, and there's huge work ongoing on maps. What kind of information you have to show on maps and how to update that and so on. So that will be another source of information for this kind of things that could happen. For the perception part, we are looking into general objects and so on that are rare and very weird objects that show up. So we are looking into that kind of problems and traffic rules and so on. The very safe solution would be that if you're not sure what to do, then you would have to stop, basically.
But what about strange signs or someone shouting that you should stop? Or, I mean, things that would stop any human driver? Or
Yeah, I don't know. It will be interesting to see. Well, it's not only this human shouting. There are other scenarios that, trolley example and so on, that people argue that, self-driving cars are not, will not be able to handle this kind of scenarios. And that is correct. I guess the expectations from self-driving cars have been a little bit exaggerated using this artificial intelligence success and so on. But it will be balanced at the end for the use cases that we have and what to expect from that. So probably we should have some fair expectations from self-driving cars. But that specific things could be handled by specific implementations also, so, but not general intelligence.
In your simulations, I've seen it's basically the area is just looking like a highway, but instead you could try to simulate it. Run the reinforcement learning algorithms on for example, say a game like GTA, maybe. That would be more helpful and more realistic. My suggestion, kind of, and what's your idea on that?
Could you please repeat the question? So we are in the simulations, we are in the highways, and then?
Yes, yeah. If instead of doing it on the highways, you could do it on a game like GTA.
Okay.
Okay.
So we are working, as I mentioned, at Zenity. We are looking into how much we can use synthetic data, not specifically GTA, but also other.
Yes, I'm just giving an example, but.
So we are looking into that, and we believe that it can be useful to a degree, but the value of real data is much more than synthetic data. But we are looking into how to balance that and how we can use the synthetic data to boost our implementations. And we have several projects ongoing on that.
So, if there are no more questions, there's going to be fika outside. Help yourselves. And thank you very much to Nasser.